All right. Good morning or good afternoon, class, whenever you're watching this video. I'm making this from my office, so it's a little bit different from the setup we have at back at my house, but same idea. Got the whiteboard we can use behind me, as well as everything we're going to be using from Canvas. So this video is for the day 7, day 8 material of our schedule. So we just had the test one, and completing that from chapters 1 and 2, we're now going to be looking at chapter 3, where chapter 3 we're going to take a little bit of a break from the statistical analysis we've been talking about, and instead we're going to look at the some intro basic probability concepts, which we're going to need before we can go into some of the deeper statistical analysis techniques that we're going to see in later chapters. All right. So chapter 3 is all about probability. And to get us started, we're looking at sections 3.1, 3.2, and 3.3 today in this video. All right. So we'll go ahead and look at that. Of course, as always, if you have any questions about the material, please feel free to email me, come by office hours. Happy to talk about any concerns you may have, whether that be homeworks or questions about the test, so on and so forth. Any of that kind of stuff is, a valid thing to talk to me about. All right. With that being said, let's go ahead and look at our material for today, starting in section 3.1. And I'll start here with sharing my screen. Actually, I forgot to share my screen. Uh, Here we go, screen 1. All right, we're sharing the screen. So again, just looking at the course schedule here, we're going to be starting in chapter 3 after test 1 here. And as we continue in chapter 3, then that'll give us what we need for some basic probability, and then in chapter 4. All right. Now we do have the Easter break coming up, so there will not be any lecture material for those days. So take those days as a break, take a breather. You don't have to work on anything. Or you can use that time to catch up on any material if there's homework or lectures that you've missed or want to go back and make sure you're ready for the material. You can also use that time to backtrack and catch up on anything you might have missed. Okay. So for this video, this is the day 7, day 8 video. We're looking at sections 3.1 through 3.3. And so for 3.1, we want to talk about some basic probability. And first, the question is, well, how do we even talk about probability, right? We need some kind of experiment where something random is going to happen. You roll a set of dice when you're playing Monopoly. You don't know what the results are going to be as you roll the dice. You flip a coin. The coin could land on heads or tails, but we don't know what's going to happen. There's some randomness at play. And so when it comes to intro probability here for this chapter 3 section, the idea is, well, how do we assign numerical probabilistic ideas to this in terms of what's the likelihood of these different outcomes? How likely do I expect to get a heads? How likely is it that I'm going to get a 6 when I roll my six-sided die? These are the kind of questions we're going to start with as we go into chapter 3. All right. So first, what is an experiment? Well, we have this definition here given to us in the textbook. An experiment is just some act or observation, whether I'm rolling dice or flipping a coin, or I'm looking at the sky and I'm watching the clouds go by. There's some kind of thing that's about to happen where the outcome is unknown, where the outcome is I can't predict it with certainty, right? I mean, I can look at the sky, but I don't know, like, well, what is the cloud going to be shaped like that pokes out of a tree or pokes behind a tree? Um, is it going to rain now or is it going to rain tomorrow? Could it rain in an hour? I can't predict that with certainty. Um, and so there's this uncertainty that we're trying to measure with these kinds of experiments, right? For a given experiment, then, a sample point is a single possible outcome in our experiment. So we can go to the whiteboard here. So let me turn off the screen share. All right. So a possible experiment we could be talking about would be rolling a six-sided die. So consider the experiment where we roll a six-sided die. Well, what could happen? I could get a 1. I could get a 2. I could get a 3, 4, 5, 6, so on and so forth. Each one of those numbers is a single possible outcome, or in other words, a sample point. So a single possible outcome is a sample point. All right. And so then the sample space is the set of all possible sample points. So in this case, for this example, the sample space, which I'll use the letter S to abbreviate for a sample space. The sample space then is a set of all possible outcomes where I can get a 1, 2, 3, 4, 5, or 6. All right. And so this is kind of a first step in the world of probability where if I want to determine the likelihood of some outcome, well, I first need to know what can happen, right? List out the possible outcomes. If we know what all can happen, that's kind of a starting place of, okay, well, now that we know this, can we consider the likelihood for an individual sample point or another sample point, so on and so forth, okay? Now, with this kind of question, you can probably already guess as we're thinking about this, with a 6-sided die, assuming it's a fair die, so we're not talking about like gambler's dice or some other die that might be unfairly weighted to favor one number or another number. Assuming it's a fair 6-sided die, like you would have in Monopoly, it's equally likely to be any of these numbers, right? So in terms of actually calculating probability, our first kind of natural instinct, natural understanding is the probability of something is the number of ways it can happen divided by the total number of possible outcomes. So the probability that I get a result of 1, well, that's only one outcome, right? There's only one sample point with the number 1. So there's only one way for it to happen. Number of ways outcome can happen. And we'll see other examples where this distinction is going to make more sense. In this case, rolling the number 1 from a 6-sided die, there's only one way to get the number 1, right? Divided by the total number of possible outcomes. If they're all equally likely, then I'm dividing this space or this probability space equally among all the possible outcomes. Number of outcomes. And so maybe no surprise, the probability of getting a 1 on a 6-sided dice is 1 out of 6, 1/6. Okay. So this gives us kind of a first little glimpse into how this works. Now, why would we be caring about this number of ways an outcome can happen? More generally, sometimes maybe we don't care about a single outcome. Maybe there's a set of possible outcomes that we would consider to be desirable. You know, if I'm playing Monopoly or something, then sure, maybe I would like to get a 6, but so long as I'm getting like a 5 or a 6 or a 4, 5, or 6, I'm happy. That's a big number, right? I mean, sure, 6 is the best if I'm trying to like go fast around the board, but getting a 5 is still a pretty high number, right? So an event is a set of sample points, which so it could contain more than one sample point. An event, excuse me. Ah, hold on, let me make sure the microphone is still connected. It is. All right. So an event is a set of possible outcomes. It's a set of possibly multiple sample points. Is a set of sample points. All right. So in general, I could, for this example we're working on, I could define a set E. And when we're talking about a set of stuff, we always use the curly bracket notation. So I can have a set E of the numbers 5 and 6. So I have two numbers here, which I am including in this event, and it has two sample points. Well, now if I ask, what is the probability of E, return back to our formulation we wrote out here. The number of ways some outcome can happen divided by the number of total outcomes. E has two ways it can occur. This event has two sample points, two different ways for E to happen. So that would then be 2 out of 6, or in other words, that would simplify to 1/3. So when we're talking about events, it could still be a single point, but an event can have multiple sample points contained in it in the same time. So as we're looking at this kind of like introductory set theory, when we're talking about these events and these sets, generally you can, in an abstract sense, you can think of it as like a bag of stuff. E is just a bag of whatever sample points we happen to care about. It's got 5 and 6 inside of it. Or if I take a different event, then it has some objects in it, depending on what sample points are of interest for that particular event. Okay. So let's come back to the textbook here. So I'll share my screen again. Sharing my screen. Here we go. Okay. So an experiment, sample points. So flipping a coin is also a great example of one of these cases where, well, it's equally likely to be heads or tails. But if I'm flipping a coin twice, well, now I have kind of multiple things that are happening, or I'm taking multiple actions in the same experiment. I flip a coin once, I have a result. I flip a coin a second time, I have another result. And so in this regard, we can create a tree diagram, which is as shown here in the textbook, where I have this branching off from each possible choice, all right? And we can also mix and match this stuff. You know, I could flip a coin and roll a six-sided die. It doesn't have to be the same type of object that we're taking some kind of action with. We could have a mix of different objects where some kind of randomness is occurring. All right, so I've erased the board back here. So let me share my screen, or yeah, let me turn off the screen share so we can come back to the whiteboard. And so I could have an experiment where maybe I flip a coin and then roll a six-sided die. All right. So in terms of listing out the sample space, all of the possible sample points, I can use tree diagramming here, where at first I flip a coin. Well, as I do that first coin flip to start, I have two outcomes, two possible outcomes. I don't know which will occur, but it could be heads or tails. But then here, as I'm drawing the rest of the tree diagram, we're kind of imagining a hypothetical future. Well, what if I did get a heads? Then what could occur after that? If I had a heads first, and then I roll the six-sided die, well, that could be a heads, followed by 1, 2, 3, 4, 5, or 6. Similarly, well, what if it was a tails first? Then I could have tails followed by 1, 2, 3, 4, 5, or 6. So we can use a tree diagramming method like this to draw kind of this map out for all of the possible sample points in this experiment. So now my sample space would be heads and a 1, heads and a 2, heads and a 3, heads and a 4, so on and so forth, listing out all of these final possible outcomes out of this tree diagram, where I'm just tracing back the outcomes as I go back to the root of the tree here. All right, and so I can write out, in this case, there are a total of 12 possible outcomes if I roll a coin and then, or flip a coin, not roll a coin. If I flip a coin and then roll a six-sided die. Okay. So we have that as a tool when we're trying to list out a sample space for a possible experiment. We've talked about sample space, so we're good there. Um, Now, when we're talking about probability, though, there are some key points that we need to go ahead and highlight here before we continue. First of all, probability, if we're thinking about like a percentage, it is 50% likely it will rain tomorrow. There is a 20% chance it will snow tonight, whatever kind of probability we're talking about. All of these probabilities should always be between 0 and 100%, right? We're never going to have a negative percentage. That doesn't make sense. We're never going to have a percentage over 100. I wouldn't say, yeah, there's a 120% chance it's going to rain. That doesn't make sense either. If you're already at 100%, then it's going to rain, right? So in that kind of situation, as we're talking about probability, we have this requirement, a rule for all probabilities that each probability for a single possible outcome must be between, if we write the percentage as a decimal, then it has to be between 0 and 1. Now, what also must be true at the same time is that when we look at the entire sample space, this is supposed to encompass every possible outcome, right? The sample space is the set of all of the possible sample points. And so if I were to take a sum of all of those probabilities all together, if that's 100% of what can happen, then the sum of all that should be 100%, right? If it's a true sort of probability space, it has to follow these two rules, okay? So that's always going to be a requirement, and that can sometimes help us figure out unknown values. If we know the other sample points, but there's some other unknown, then we can find the unknown based off of what we do know. So a great example of this would be, consider, yeah, and actually, before I show example 3.4, let me do this on the board, but I'm going to leave some information out, and we'll see how those properties we were just looking at can help fill in the information. All right, so let's look at a different experiment where, let's say, we are now dealing with an unbalanced coin, an unfair coin, where the coin has been tampered with, it's been weighted in some way such that when you flip it, it favors one side over the other. All right. Now, the question doesn't tell us how they're unfavored or favoring one side or the other. It just says, consider flipping two unbalanced coins, right? Where we're also told in terms of, okay, well, first of all, what can happen if I flip a coin twice? From our tree diagramming, we know, well, I could have two heads, I could have two tails, I could have a heads then followed by a tails if I got a heads first, or maybe I got a tails first and then a heads. So there's two different ways to get one of each, but I am listing both sample points as the difference is the order in which this stuff is happening. So these are two different outcomes since these things happen in a different order. They're different possible futures, okay? But now as I look at their probabilities, probabilities, right? Probabilities. Yeah. Because it is an unfair situation, an unbalanced situation, then I'm not just going to have equal probabilities here. In this case, in the case of this question, they actually tell us the probabilities for us in a table where they say heads has 4 knights, heads tails has 2 knights, and heads tails also has 2 knights. Okay. Now, the question in the textbook also tells us about tails heads. However, Whoops, I made a mistake here. Sorry. Heads, tails is 2/9, and tails, heads is 2/9. They're both the same, which makes sense since that's one of each. But now tails, tails. Now again, in the textbook, it does tell me what tails, tails is, but without looking at the textbook, we can actually figure out what this number is supposed to be. How do we do that? Based on those probability rules that have to be true, which we just saw a moment ago. If this is 100% of what can happen, if this is 100% of all the sample points, then all my probabilities have to together add up to 1 if that's 100% of what can occur. Well, in which case, I have 4/9 plus 2/9 is 6/9 plus 2 more ninths is 8/9. I'm only missing 1/9 to make the whole thing add up to 1. And so I'm able to fill in the blank of this unknown because all the probabilities have to add up to 1. Now, of course, yes, if you're looking at the textbook, we already knew it was going to be 1/9 because that's what it says in the table. But the point I'm trying to make here is that even if we didn't know that, we could have filled in the blank based on the other information. All right. And so you may see some exercises like that in the homeworks for chapter 3 here. Okay. So we can create this probability distribution, which is given to us in the textbook. It has some different events where we do want to make a distinction here between the events A and B. So the exercise says, well, let A be the event that we observe exactly 1 heads. It doesn't care when or how it happens. It just wants exactly 1 heads. And B is the event where we observe at least 1 heads. Right? These are, in fact, 2 different events. If I look at A here, well, in order to get exactly 1 heads, there's only 2 ways for this to occur. That means I got a heads, tails, or a tails, heads. But the event B, because of the word at least, not only is it including the case where I have 1 heads, but it says at least 1 head. So I could have more than 1 heads, in particular the case of when I have 2 heads. All right. So in this case, because B does have more sample points here, in fact, while they share the same sample points, B has the same points as A, plus an extra point, we already know B is going to be more likely to happen. There's more ways for B to occur. But if we add up these probabilities, we can find the probability of A. Well, now we got to be careful. This isn't just 2 out of 4 because each sample point has a different probability associated with it because they are unbalanced coins. And so as we're doing this, to find the probability of an event, we can add up the probabilities of the individual sample points. So the probability of heads, tails is 2/9. Probability of tails, heads is also 2/9. And so the probability of A is 4 out of 9. But if we're looking at B, well, it has those same points as before, so I'll just write 4/9 for heads, tails, and tails, heads. But it also has heads, heads. So it has another 4/9, and so B has a probability of 8 out of 9. All right. And so we're able to calculate the probability of these 2 individual events by first finding all their sample points, and then once we have their sample points, we can add up the probabilities of those points which are contained in each event to get our final answers. Okay. So we have that example here from the textbook. Oops, let me make sure. Oh no, that went a little off the camera. Let me move that slightly. Okay, there we go. Yeah, so we get 8/9 for the probability of B here. All right. So let me go back to sharing my screen so as we're looking at the textbook here. Okay. So this is going to wrap up section 3.1 for us, where in summary, we have the steps for calculating probabilities regarding an event. First, okay, we have some experiment which is defined for us. Once we have that experiment, then we can list the sample points. Once we have the sample points, we have probabilities which are assigned to each individual sample point. If they're all equally likely, then the probability of a single point is just 1 divided by the total number of points because they're all equal, they're all equally likely. They are then sharing the probability space equally between all the sample points. All right. So we assign the probabilities. Once we've done this, then whatever event we have an interest in, we need to determine what sample points are in that event. And then lastly, once that's been determined, then we can take the probabilities of each of those sample points contained in the event and add them all up together. This allows us to calculate the probability for any event we could possibly like to think about. Now, there's a little bit of trickiness here where depending on the experiment, because in the case of what we did here, there were only 4 outcomes, right? In the case of rolling a 6-sided die, there were only 6 outcomes. So it was easy enough to write it all out by hand, all right? But in the real world, oftentimes when we're trying to determine something about some random situation, there may be many more, hundreds, thousands of possible outcomes, in which case this does become a trickier question to answer. All right. So we'll see more how to handle those situations as we continue in chapter 3, but this gives us a good start with section 3.1. All right. Okay. So we want to, one last point of 3.1 is this kind of counting game where we already know that the number of possible outcomes could be a tricky situation, right? In this case, there were only 4 outcomes. In the case of a 6-sided die, there were only 6 outcomes. But how do I know how many outcomes are possible? Well, on one hand, depending on the situation, the experiment, we can calculate this as a combinations question. Okay, so what does this mean? Well, first, when we say combinations, you can imagine, if I have a bunch of ingredients where I'm going to make a sandwich, or maybe I have ingredients that I can put on a pizza, then the order in which I put the ingredients on the pizza is not actually going to change anything, right? If I put onions on a pizza and then I put pepperoni on the pizza, that's a pepperoni and onion pizza. If I put pepperoni on the pizza first and then onions, it's still a pepperoni onion pizza, right? Now, sure, the order in which I put them on the pizza was different, but it's still the same produced product, right? It's still an onion and pepperoni pizza, okay? And so combinations, or this rule for combinations, is specifically used when we're trying to count the number of ways that we could pick things where the order does not matter. All right. You can also think about like if I'm trying to create a committee, I want to create a party committee for the statistics class. All right. Well, then this committee, maybe I would pick random names out of a hat, right? And maybe I would pick Bob out of the hat. And then I would pick, maybe I reach in the hat and I pull out Emily. And I have Emily and Bob, right? Well, regardless of the order I pick those names, if I got Bob first and then Emily, I would have a, so let me switch to the board here as we're talking about this. Turn off the screen share. So if I had an outcome where I had Bob and Emily, and I'm going to use the two of them to make my party committee. They're going to be in charge of that. They're going to plan what's going to happen with our parties, and so on and so forth. But if I draw Emily's name first and then Bob, well, these aren't two different committees, right? This is the same committee, just because I flipped the names around. It's still the same committee as Bob and Emily, right? These are the same committees, right? And so in this regard, this is what combinations is all about, where if I have, and to use the notation they're using in the textbook here, if we have an n number of things to pick, n number of objects to pick from. So capital N is the number of objects to pick from. Right? It's the number of objects to pick from. Now, it could be living things, like we could be talking about people. If I have 10 people in a class or 15 people in a class, then capital N would be the total number of people that I'm picking from to form my committee. Then we use lowercase n to be the number of picks made. All right. Number of picks made. Then this would be like if I'm picking 2 names for a committee, or if I'm picking 3 names for a committee. I may not pick all of the n possible choices, but I'm going to pick some number of them. All right. So lowercase n is generally for combination formulas like this and for combination application questions, little n is always going to be less than or equal to capital N, right? I can't pick more objects than the number of objects I have available. If I have 20 people in a classroom, I can't pick 25 people. There's not that many people. So lowercase n is always less than or equal to capital N, right? So how do we actually determine what are the total number of possible committees? What are the total number of possible outcomes? Well, if we think about the tree diagramming for a moment, then as I start with capital N, when I first pick a name out of the hat, if there are 20 people or 10 people, or just make it easier, like for this online class, let's just say maybe there are like 7 people to pick from. So the first name I draw out of the hat, I'm going to have 7 possible outcomes. Right? I could have person 1, person 2, person 3, person 4, person 5, person 6, or person 7. Now, once that name is pulled out of the hat, I'm not going to pick that person again, right? I couldn't have a committee of Bob and Bob with himself, Bob again. That wouldn't make sense. So as a name is picked out of the hat, we're not going to put the name back in. So this is picking from the capital N number of objects without replacement. All right. But then the next step, well, there's 1 fewer, so I would have 6 choices to pick from. And now I'd have 5 choices and 3 choices and 2 choices and so on and so forth. So as I'm thinking about this tree diagram, which is what we used earlier for mapping out a set of possible outcomes, I would have 7 choices. And then for each one of them, there would be 6 names that could be picked. And then after that, there could be 5 choices, so on and so forth. And so the tree diagramming here is going to result in 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, if you've seen this before, this is exactly what mathematically a factorial is. The number 7 factorial is 7 counting down multiplied with each number less than itself as it counts down to 1. So 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, so on and so forth. All right. So this would show me all of the possible outcomes from tree diagramming, right? However, we'd already said that Bob and Emily is no different than the committee from Emily and Bob. So if I have 7 people to pick from, how many committees of 2 could be made. Now, unfortunately, the answer is not just 7 factorial, because this here is like, well, that's if I'm picking all the names of the house out of the hat until it's empty, right? I'm not making, in this case, there'd be 6 different choices or 7 different choices. I'm going to stop picking names after I draw the second name. So I would have 7 choices at first. I pick a name out of the hat. And then I would pick a second name. The second name, I would have 6 choices, and I would stop. This 7 times 6 times 5 times 4 times 3 times 2 times 1 is if I kept picking until the hat is empty. All right. So for my formula then, how many different ways can this happen? 7 factorial would be if I picked until the hat was completely empty, right? But I don't want to do that. I actually want to stop after I make the first 2 choices. I'm not going to pick more names in the first 2, right? So we always divide by 7 minus 2 factorial. Now, why are we doing this with our formula? 7 minus 2 is I'm making 2 picks. 7 minus 2 is 5. This will divide out 5 factorial down, right? If 7 factorial has 7 through 1, then 5 factorial has 5 through 1. As I divide, it'll cancel out that 5 through 1 from the top. All right, which is good. We want that. Now, the only other issue, though, is that while that cancels out the 5 down to 1, when I have this 7 times 6, I'm still double counting. What if I had Bob and Emily up here? Or what if I picked Emily first and then Bob? There's 2 different ways that could occur, but that is the same committee, right? I don't want to double count the same committees if I'm trying to list out all of the possible different committees that could be made. And so for a combinations formula, we have to also divide out this possible double counting. In order to do that, that's always going to be the number of choices we're making factorial in order to cancel out all of that double counting. And so for our answer for this question, in the numerator, I'd have 7 factorial, so that counts down. In the denominator, well, I have the 2 factorial. 7 minus 2 is 5 factorial. And 5 down can cancel out from the top and bottom. So that's nice for us. All that's left is 7 times 6 divided by 2. But 6 divided by 2 is 3, so we have a total of 21 different committees that can be made. If I have 7 different people, then I'm going to make a committee of 2 of those people. So the punchline, our combinations formula is given by the following calculation, where we have N, capital N, is the number of objects I can pick from. Lowercase n is the number of picks I'm going to make. All right. Where first, well, capital N, if I do capital N factorial, that is the total number of possible outcomes if I fully draw all n, all capital N, of my possible objects. If I draw all of them, how far can I go until there's nothing left to pick? That's what the numerator is. But I'm not going to be making that many choices. Whatever n is, well, n minus lowercase n. So like when capital N was 7, lowercase n was 2, this subtraction is cutting off all the rest that we're not going to be picking, right? If I'm only making a lowercase n of choices, then n minus n, whatever that difference is, I'm not going to make all of those choices, right? I didn't make choices beyond the first 2, and so I had 7 times 6, but then 5 down, I can cut off. I can stop. I'm not going to make more choices after that. All right. But then lastly, we also have to divide by lowercase n factorial in order to cancel out possible double counting. And so this gives us a formula. Whenever we're trying to find the total number of possible combinations for an n number of objects to pick from, where we make an n number of picks, an n number of choices, and we can do that with this formula, right? Now, a key point here, like we said at the beginning, was that for this combinations formula to really work, we're making the assumption that the order in which the objects are picked doesn't matter, all right? Now, there are some things where this doesn't make sense. If I'm trying to list a number of passwords for something. For a password, if you have ABC versus BAC, well, that's different, right? The order of the stuff matters in that case, so that is not a combinations question. This formula only works where the order in which I list the objects doesn't matter, right? Like forming a committee or putting ingredients on a sandwich. A peanut butter and jelly sandwich, whether you do peanut butter then jelly or jelly then peanut butter, it's still a peanut butter jelly sandwich, right? Now, sure, maybe we could get into the debate of like, well, what's the proper way to make a peanut butter and jelly? Not worried about that for today. We can debate that another time. But the point here is just when we're doing a combinations calculation, there's this assumption that the order of the objects, the order in which they're selected, does not matter. All right, and so we can use this formula anytime we're trying to calculate a number of combinations, number of possible combinations. Okay, let's see. Yeah, so they all fit on the board. I just double checking the screen, make sure everyone can see that. All right, so where are we going from here? Let me share my screen again. Okay. So this wraps up section 3.1. We're now going to look at section 3.2, where we want to talk about the unions and intersections of events. Now they give a definition here, but I'm gonna put this on the board. I think that'll be more helpful. So we already know from what we did in 3.1, we calculate the probability of an event by finding all of its sample points, find the probability for each of those sample points, and add up all those probabilities. But what if I have two different events and maybe I want to mix them together? I have a bag of possible outcomes over here. I have a different bag of possible outcomes. And then I want to mix them together. I'm going to dump them into the same bowl together. And now I have this larger bag with all of that stuff all together. Now what's the probability of that outcome if I mix multiple events? So this is called a union when we're mixing events together. So the union of two events, A and B, A or B, is satisfied when either A or B occurs. Keyword being here or. So when we're taking the union of two events, this is like the word or. You go to the store or you go to an ice cream parlor and they ask you, would you like vanilla or chocolate in your ice cream cone? And you can get one or the other, and that satisfies the question. That satisfies what is being told to you, right? Now, you could get both. You could be like, well, give me one scoop of each, right? So it could be the case that both events are occurring, but with the word or here, we're not requiring that both happen at the same time. So long as one or the other happens, then a union is happy. Right? In other words, when we take a union of two events, if we're using Venn diagram notation for a moment. So let this rectangle be the sample space, the entire sample space of all possible outcomes. And the event A, I'll use this circle to represent A. And maybe I have a different event B. Maybe they have some overlap, maybe they don't. But whatever is going on here, when we say take the union of A union B, so when we talk about unions, we use the capital, or it looks like a capital U, sort of. We use this symbol to when we're talking about a union between two events. This would mean that I'm taking everything in A, I'm combining it with everything in B, and I'm just lumping them all together into a single event. All right. So we could have something like, consider the six-sided die example again. So roll a six-sided die. Okay, let A be the event that I have a 2 or 3. Let B be the event that we have a 3 or 4. Then the union of these two guys is to say, well, if I take these two different events, these two different bags of stuff, bags of sample points, take them, dump them in together into the same bag, and this is the same event. So what happens? Well, I have all of these points all together now. Now you'll also see I'm not going to double list 3 because 3, after all, that's just a single sample point, right? I don't have multiple 3s running around. There's just one 3 as a possible outcome from this experiment. And so while 3 is listed in both events, when I take the union, I'm just writing out all of the sample points which are in A or in B, right? And so A union B is 2, 3, 4. Again, part of the key here we really want to highlight here is that unions are associated with the word or, right? I'm happy if A or B happens. They don't both have to happen at the same time. So if I roll a die and I get a 4 and I say, well, you win if A or B happens, then that would be a win, right? Even though A didn't occur because of the word or, we're happy if either one of them happens. Okay? Now, as we talk about an intersection, this is kind of the opposite situation where now I want both to occur at the same time. The intersection is associated with the word and. So let me just erase what I have here. And we'll see how this definition is modified. So as we're talking about the intersection of two events A, B, the intersection is satisfied when instead of either, we're saying both. So the intersection of two events A, B is satisfied when both A and B occur. So when we're taking an intersection, then this is the space where A and B share things in common, where both events have to happen at the same time in order for the intersection to be happy. And for intersections, instead of the union symbol, we just flip it upside down. And this is our intersection symbol. Me personally, I tend to remember this symbol because it kind of looks like an N, and we have the letter N in intersection. All right. But for our example over here, now as I take the intersection of A and B, instead of saying, well, what are the possible sample points which satisfy A or B? What are the sample points which satisfy A and B? I want to know what points do they both share in common? What point would allow A and B to happen at the same time? In this case, they only share the sample point 3 in common. So rolling a 3 is the only way that A and B could both happen at the exact same time. So we have the distinction between a union and an intersection. Now, I also want to highlight here, you might already be thinking this, an intersection isn't necessarily going to have stuff in it. I mean, after all, if I had different events, like what if A was the event of even numbers and B is the event of odd numbers? Well, then their intersection, there's no number that's both even and odd on a six-sided die. And so it would be impossible then for both A and B to be satisfied. And so sometimes when you take an intersection, that intersection might result in an empty set. Now, in this case, it wasn't empty, but that's just something that could happen when you're dealing with this kind of set theory operation. All right. So we have that. Let me come back to the textbook here. So I'll share my screen again. Right, we have unions. We saw that on the board. They have this picture here, which is the same picture we saw on the board, where a union means both are happening at the same time. An intersection, or sorry, a union means one or the other is happening. They don't both have to be happening at the same time. We're happy if either occurs. An intersection means both have to happen at the exact same time. All right. And they give an example here, kind of going step by step through how we can think through this process. I don't want to go through all this right now as we just did an example on the board, but this is also kind of just good additional practice if you're wanting to look back at this as well. All right. Okay. So skipping over that. So where we want to end today is in section 3.3 with the idea of the complement. Now, when we say the word complement, I want you to think not. So the complement of A is everything which is not in A. In other words, it's the opposite of some events, everything not contained in that event. So in terms of a Venn diagram picture, and so I will turn off the screen share to go to the board again. When we're talking about the complement, so definition, the complement, hold on one moment. All right. The complement of an event A is itself an event. The complement is also an event. It's just an event with all sample points which are not, being the key word, in A. So in terms of my picture, if this rectangle is the entire sample space, and if A is this circle, and this circle is all of the points inside of A, then when we say A complement is everything not inside of A. In other words, it's everything outside of A, right? So A complement, for the textbook and in homeworks, you'll often see this notation where they use A raised, it looks like A to the C power. We just use notation to say that we're talking about a complement. All right, this is the complement of A. And so this is, these are the sample points. It contains sample points, which are not in A. Okay. And so as an example, if, again, we're thinking about rolling a six-sided die, and then let A be the event that we have a 2 or a 3, okay? Then A complement is all of the sample points which are not in A. That would be 1 and 4 and 5 and 6, okay? Well, okay, so what? Why do we care about the complement? Why is this useful? Well, this kind of right away gives rise to a special rule in probability called the rule of complements, which just states if you have the probability of some event, whatever A is, and you add it with the probability of A complement, what does this mean? Well, because A and A complement are containing these sort of opposite sets of points, take a look at the picture. If I have everything in A, and this is in black, got all the points in here, which are in A, and then in red, I have all the points out here, which are in A complement. Well, together, I've highlighted the entire sample space, right? Everything in my sample space is either inside of A, or if it's not in A, then it's inside of A complement, right? Every single point is in one of these two sets. Same thing here with the six-sided die question. I have these points here which are in A, and then everything else is A complement. So what's nice about this is that the probability of an event plus probability of its complement is always equal to 1. This fact can be super handy dandy when it comes to trying to find probabilities, especially if we consider maybe the event I'm looking for, if it has hundreds or thousands of ways that A can happen, that could be a lot of work to write that out by hand, right? Where instead, if A complement, if it only has a few ways to happen, then that might be easier to find and easier to calculate. If you can find one of these guys, then using this equation, we can use that to solve for the other. All right. Now we're going to have an example of this showcased in our participation question for today. So let's go ahead and take a look at that. This is participation day 8 in Canvas. And so I'll stay on the board for right now as we're working through this question. But you can see the question in Canvas for participation day 8. And let me keep the rule of complements here as we're going to need this in just a moment. Probability of an event plus probability of its complement is equal to 1. Right? Now, we're considering an experiment where we toss a fair coin 10 times. So we have this experiment where we toss a fair coin 10 times. Now, if we're thinking about the tree diagramming here for a moment, when I toss the coin the first time, I could get heads or tails. There's 2 possible choices. But for each one of those, if I got heads first, then I flip the coin the second time, it could be heads or tails after that. But if I had tails the first time, it could be heads or tails after that. Well, we see this multiplication thing happening, where I had 2 possible outcomes, and the second flip, 2 more possible outcomes, but that's 2 more based off of the first outcome. So I have 2 times 2. Then the third flip. Well, I got to multiply by 2, so on and so forth, and it's kind of too big for me to draw it here on the board. But you may be able to see what's happening here. I have 2 to the 10th possible outcomes as I branch 2 times, and then branch 2 more times, branch 2 more times. I do that a total of 10 times, I branch out. And so I have 2 to the 10th, or if we go to a calculator, 2 to the 10th, we have 1,024 possible outcomes. Right? I have 1,024 possible outcomes here, which is a lot. Okay. But now let's go back to the question. The question says, let A be the event that we observe at least 1 heads. At least 1 heads. Okay. Well, what's the issue here? Well, I could list all the ways I could get 1 heads. That would be 1 heads and 9 tails. but did I get that one heads on the first toss, or the second toss, or the third toss, or the fourth toss, or the fifth toss? There's a lot of ways to get one heads. Or, because it's the word at least, what if I got two heads? What if I got three heads? What if I got four heads? What if I got five heads? So on and so forth. Trying to write all of this out for the event A is going to be a huge headache. And we already know if there's a total of 1,024 possible outcomes, that's going to be pretty hard to do by hand, right? That sounds terrible. This is the perfect case of, well, maybe the complement is easier. So look at this. What is a complement? A complement means not A. So think about the opposite here. What if I say not at least one heads? Well, to say not this, that would mean I have 0 heads. Since A is satisfied by having any number of heads, so long as it's bigger than 0, it could be 1 through 10, right? This means the complement, this is the case of where no heads occur. Well, now that's much easier to find. In fact, there's only one way to get no heads. That means a complement is the event with the sample point where I got tails 10 times in a row. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's only one way for the complement to happen, where I got all tails. Well then, lucky us, the probability of a complement, because all the outcomes are equally likely, this is a fair dice, or it's a fair coin, then this means the probability of the complement is 1 out of 1024. But now go to the rule of complements. I'm not trying to find the probability of the complement. I want to find the probability of A to answer the question for this participation day. Well, if the two properties or probabilities are supposed to add up to 1, then plug in what we know. The complement is 1 over 1024. And whatever the probability of A is, that plus the complement is supposed to add up to 1, so that's 100% of what can happen. Then the probability of what we're actually looking for is 1023 out of 1024. And that will give us our answer for this video's participation question. All right. So I'll leave it at that for today as we've gotten into chapter 3. If you have questions on any of this, of course, feel free to email me, come by office hours, let me know. I'm happy to talk about any concerns you might have. So this we'll continue in chapter 3 in the next video, but for now we'll stop there. Best of luck. Let me know if you have questions, and I hope you all have a great rest of your day. All right. See you in the next video.